Hello all, here we go with section 1.2, our second section in our first topic, which is looking at energy, power, and society, work, energy, power, and society. And we're going to start with some homework from last night. Last night I left you with questions 1 to 11 on page in the review for section 1.1. When I went back to look at those questions, I thought I really don't like some of those questions. So if you haven't done them all, if you've done them all, that's terrific. If you haven't done them all, I'm going to leave you with just the ones that I've listed here, which are questions 1 to 8, but not 6. So 1 to 5, 7, and then 7 and 8. As I was working through the textbook today, I'm looking at our textbook, and there's a lot of good questions in our textbook that I think may actually be better than some of the ones that are in the package that I handed out. So I'm going to really suggest that you take your time and work through the questions here that are in our textbook, which is the Irwin textbook that I handed out to each of you. Hopefully you've got it at home. So there are the 4 questions that are samples. These examples are all done for you. I encourage you to read the question and try them yourself. And then just, if you get stuck, you've got the textbook there to help you with those 4. And then there's another 11 questions there on page 242 for you to try. So for now, I'm going to start with question 7 up here. Oops. I'll start with question 7 up here from the homework last night. So let's go to our whiteboard here. In question 7, from section 1.1, it's got a person pulling up a bucket, which is 2 kilograms. And is pulling up the bucket using a rope. Okay, so FT, remember from our last unit, T is tension, which means a rope. And I also have, as always, gravity acting on this. Let's just do this now because you know we're going to need it. mg, which is 2 times 9.8, which is 19.6 newtons down. Okay, so a rope pulls up a 2 kilogram bucket straight up, accelerating it from rest. Also, we're given some kinematics data. V1 is 0, at a rate of acceleration of 2.2 meters per second squared. For 3 seconds. Okay, so I'm seeing I've got enough information there to calculate delta D or to calculate V2. Part A of the question, 7a, says, what is the displacement? Look at that. So for part A, it says, what is delta D? So I'm thinking I'm going to use my V1 delta T plus 1/2 A delta T squared. Historically, everyone in my classes has known that this is my favorite equation, so I always say I'm going to use my favorite equation. V1 delta T is 0 because we're starting from rest, plus 1/2 the acceleration, which is 2.2, times my time of 3 seconds squared. Half of 2.2 is 1.1, times 9 makes 9.9 meters. Okay, and it's going up because it says the bucket is being pulled straight up. Okay, question 2 says, calculate the work done by each of the forces acting on the bucket. So if I look at the forces that are acting on the bucket, I can see that gravity is acting on the bucket and the tension's acting on the bucket. But I don't know what the force of tension is. So before I can do anything here, I need to calculate the force of tension. So, oops. To calculate the force of tension, again, I'm just going to do what I already know. So all of this was from chapter 4. Everything that was there we just done in chapter 4, and then the free body diagram now is going to bring us into chapter 5. So if I look at the FNet statement for this bucket, there are two forces: tension in the rope pulling it up, Ft, and the force of the planet pulling it down, Fg. I know Fnet is equal to ma, and I know the force of tension I don't know, it's unknown, and I know what the force of gravity is. Let's move this out of my way. It's negative 19.6. ma is my Fnet, which is equal to 2 kilograms times acceleration of 2.2. I'm going to take my negative 19.6 across as plus 19.6 equals Ft. So 2 times 2.2 is 4.4 plus 19.6 makes 24.0 newtons. So Ft is now known. So I've got a gravitational force pulling down on the bucket, and I've got a rope pulling up on the bucket with a force of tension. Okay. Part C of that question said calculate, B says calculate the work done by each force. Okay, so let's scroll this up a little bit. And for B, let's look at the work done by the string. It's going to be the force of the string times the distance. The force of the string is 24 newtons up, times my distance of 9.9 newtons in the same direction, and I end up with an answer of 238 joules. Okay, again, remember, it's not a vector quantity. If I look at the work that's done by gravity, okay, because remember gravity is applying a force over a distance. The force here is negative 19.6 newtons over a distance of positive 9.9 meters. And I end up with a work done by gravity of negative 194 joules. Okay, so that's B. What is the work done by each force acting on the bucket? C says, what is the work total acting on the bucket? Well, it's going to be the work of the string plus the work of the planet. Work of the string is 238 plus the work of the planet, which is minus 194, and my total work done is equal to 38 and 6, 44 joules. There's my total work done. And then D says, calculate the net force acting on the bucket and the work done by the net force. Compare your answer to what you just had here. So D, Fnet, whoops, undo. D, Fnet equals MA, which is equal to 2 kilograms times 2.2 meters per second squared, which is 4.4 newtons. And then if I find my work total because of Fnet, it's equal to Fnet times delta D, which is 4.4 newtons times my displacement of 9.9 meters, and I'm getting an answer of 44 joules, which is the same as the answer that I got by calculating the work done by the string, by the rope, and the work done by gravity, and adding those two works together, I get the total work, just like I would have done if I used Fnet to calculate my total work done. Okay, so there's question 7 from the homework. And hopefully that's helpful. I'm going to suggest, like I said, really take your time and go back and do these questions here, right? The ones that are in our textbook. Start with the samples, the examples 1, 2, 3, and 4, and then from there get into the questions. Some of the questions in our textbook are really quite tricky. If you think the ones that are in this textbook, this set of notes that I'm giving you from a different book can be challenging, some of the ones in the Irwin book, in our book, can be very challenging. I'm sure you're saying, yay, thank goodness for that. Okay, so let's move today into the second topic in this first section, this first note, or part one of this unit. Remember, there are 3 parts to this unit. The first part is all about mechanical energy and work and power. The second part of this unit is about thermal energy and heat, and the third part of this unit is about nuclear energy and power. So we're still working in part 1, we're still in the first part, but we're in the second note, 1.2, and when we talk about energy now, so if we talked about work, we talked about work is done when a force is applied to an object and moves it delta D. We also said that work happens to an object when its energy changes. So let's talk about what energy is. Energy is the ability to do work. Right. So what is the ability to do work? It's the ability to apply a force to move an object delta D, right? Or energy is going to happen when work is done to an object. So these two are basically very, very similar. The concepts of energy and work are both similar. They both have the same units, which are joules. Right? Now, ultimately, there are many, many different forms of energy in the universe. We talked in yesterday's note about the first law of thermodynamics, saying that energy cannot be created or destroyed, but there are many types of energy in the universe. All of them involve one of 2 types of energy, right? The 2 basic forms of energy are motion and energy that is stored in one way or another, called potential energy. If I said to you, you've got the potential to be the next mayor of Hamilton, if that's a good thing, I'm not sure, that means it's within you. It's in your body. It's in your constitution. It's stored in you, and that it has the potential to come out and do that. So the same thing with energy. Potential energy is stored energy. Now, I'm not going to take time to go through all the different types of energy, but there's basically a few that we're going to be talking mostly about. We're going to talk a lot about gravitational energy here, because gravitational energy deals with all the things that we normally deal with in our day-to-day world, going up and down stairs, lifting something up, standing up, lying down, throwing something, whatever it is that you're doing, we are almost always involved with gravitational energy in one way, shape, or form. We also have kinetic energy. We also have kinetic energy, which is the energy of motion. And basically, kinetic energy here, I'm not sure why it's not even on my list. No, it's not even on the list here. Kinetic energy is the energy of motion, right, which is up here already. Okay, so those are the 2 we're going to be mostly talking about. We're also going to talk about mechanical energy. Mechanical energy is a combination of the potential energy and the motion, right? So if I think about an apple falling out of the tree, it has 2 things. It has motion, it has kinetic energy, and it has stored energy, it has potential, because as it's falling, it has the ability to keep speeding up, and it will continue to speed up and convert its potential stored energy into more kinetic energy as it gets faster and faster. Okay, so we're going to talk about mechanical energy, which is a combination of those 2 things. Now, there's also radiant energy. Radiant energy is typically electromagnetic radiation, which includes visible light. and invisible light, right? Invisible light would be infrared radiation, ultraviolet radiation, microwaves, gamma radiation, X-rays. So there's a number of different types of electromagnetic waves that you are going to have seen in your ISU. They are radiant energy. There's electrical energy, and there's different kinds of electrical energy. There's static and electric energy, and there is current electrical energy, and we'll talk about both of those in our next unit. There's thermal energy, which is our next chapter. There is sound energy, and again, all these things have the ability to do different things. And remember, one of the things we know about energy is different forms of energy can be interconverted. So I know I can take any of these forms of energy and use them to make other forms of energy. Right? I can use light energy and use it to cause, let's say, a solar-powered plane. I mean, that day is probably coming where I'm going to take energy from the sun, use it maybe to create chemical potential energy in a battery. That chemical potential energy might somehow be used to create height of an airplane. Right? And mechanical energy and kinetic energy. Right? And all kinds of things happen, and maybe that battery is going to produce electricity that's not static electricity, but current electricity that's going to be used in that airplane to run the lights and to run the gauges and the dial, all the instrumentation that's in the cockpit and the computer for guidance. All that stuff will be used from radiant energy, which was the source of all those things coming from the sun to charge the batteries to run that plane. So you can see that, and maybe it's going to be creating sound energy. Maybe that's just the sound of the captain's voice over the sound system inside the plane, or maybe it's the sound of the airplane if it's making noise. And thermal energy, right? As the plane is moving, there might be friction between the either the brakes and the rotors and the calipers, or maybe between the air and the wings. But we're going to be creating thermal energy too, which is going to be heat produced by friction. So you can see all these things basically have the ability to be converted to and from other forms of energy. Now, in our textbook, on page 216, there is a similar chart. I think the chart in our textbook is probably a little more user-friendly than this one, and maybe even a little bit more interesting than this one. Okay, so those are all different forms of energy. Now, I'm going to start this unit talking about kinetic energy, which is the energy of motion. Now, when we were doing section 1.1, yesterday, we started looking at work equals force times distance, right? And that work we called mechanical work because it was causing an object. If the object isn't moving, we said, then there's no mechanical work happening. So the work here is kinetic energy. That's the work that we were talking about. Now, what we know is that an object that's in motion has energy, has the ability to do stuff, right? And if I think, well, what does that mean? It means that if I took that object that's in motion and it came in contact with another object that was stationary, it would transfer some of its energy to the other object, and it would cause that other object to move. So it would apply a force to that other object to cause it to move. Again, think about something rolling down across a parking lot and running into a person's car, right? Or anytime something comes in contact, one car coming in contact with another during a collision, right? If you've got a parked car there and another car comes along, and because it's in motion, right, it has energy. It has the ability to do work to the parked car. What it's going to do to the parked car is it's going to apply a force to the parked car and cause that parked car to move. It'll probably also rearrange some of that parked car so it now has a new shape, and some of the work that it used, some of the energy that it had, which has now been changed into another type of energy, is used to rearrange the particles in that parked car. Now, what decides how much force that can be applied by that object are a couple of things, right? If that object that's rolling has a higher mass, right, it can apply a greater force to the object. If it's moving faster, if it's moving quite slow, it may not do a lot of damage to the parked car. But if it's moving really fast, it might really destroy that parked car, or maybe send it flying across the lawn where it's parked in front of that person's house. Right? So if the car that hits the parked car has a huge mass and or is traveling fast, those two things decide how much force it's going to apply to the object. Now, what I know is two things. Okay? Work is being done because a force is being applied to the object to move it delta D, and I know that the force here is going to be mass times acceleration. Now, I'm going to basically ignore friction and ignore other forces, and let's just look at one cart running into another cart. Now, we often do this in physics in the class, where we'll take a cart on wheels and we'll launch it across the desk at another cart. The other cart is sitting here motionless. And this cart's going to come in and it's going to collide with that cart, and as it does so, it's going to cause this cart to go flying. Now we actually have a little spring bumper in here, so when this incoming cart hits it, the spring will basically compress and then expand again, and as it's doing so, it causes the parked cart to go flying, and it causes the incoming cart to slow down, if not get bounced backwards. Now, if I look at if work is equal to force times distance here, and I'm only going to focus on force being the applied force being the only force, then F net equals Fa. And if F net is equal to Fa, then I can take this and substitute it in here to give me work is equal to mass times acceleration times delta D. Now, what do I know about displacement? Well, the displacement, if I use the one formula that we had from chapter 2, the one formula says displacement is equal to V2 squared minus V1 squared over 2A. If I take the A from here across to the side of the delta D, I get A times delta D equals V2 squared minus V1 squared over 2 here. And now if I look at the fact that the object that was hit was at rest initially, then this V1 becomes 0, so I've got V2 squared minus 0, which is V2 squared, and I end up with A delta D equals V2 squared divided by delta T. Now, if that's the case, if I know that A delta D equals V2 squared divided by 2 from my kinematics from Unit 2, and I'm now going to plug A delta D in here where I have my A delta D, I now get the work is equal to mass times A delta D, or work equals mass times V2 squared over 2. Okay, work equals mass times V squared over 2 here. That work that was done to the object that was parked is now the kinetic energy that it has. Assuming that it had an initial velocity of 0, its new kinetic energy, its energy of motion that it is carrying with it, right? It has the ability, if it collides with something, it will transfer its energy to something else, right? So it has the ability to do stuff. That's what energy is. So my work here is equal to m times v2 squared divided by 2. The units here are going to be the units that we had for work, which are in joules, right? Force times distance, and our energy units are in joules. So if the work here is equal to EK and work is in joules, then EK is now in joules. And we often take this equation, and instead of saying mv squared divided by 2, it's usually written in most textbooks as half mv squared, where the v is the v that the object has compared to when it had no velocity. All right, so if a car or an object is moving, or a bicycle or a skateboard or a baseball is moving, right, the speed that it's traveling at, right, gives it kinetic energy, which is compared to 0 kinetic energy when it wasn't moving. Okay, so let's look at how we use this equation. So if I look at 1.2, the sample problem, so if I look at 1.2a, and this is the sample problem, that's in the other document. Remember, there are 2 documents for this unit. One are the notes, which are the one I'm working through right now. The other one is the one that's got all the questions. So again, if I was to just switch to the Unit 3 samples and homework, you would see that I am here right now, section 1.2a, the sample problem. And then these are the 3 practice problems here that I'm going to leave with you in a minute. Okay, so 1.2a sample problem, it says, calculate the kinetic energy of a 150 gram baseball traveling towards home plate at a constant speed of 35 meters per second. Okay, so my given information is my speed at 35 meters per second. We're told the mass of the baseball, come on you, 150 grams. I know 1 kilogram is 1,000 grams. Wow. Not sure why sometimes this stylus works, sometimes it doesn't. So my mass now is 0.150 kilograms, because my masses always have to be in kilograms for these equations with in this unit to work. So just like my speed in the past units cannot be in kilometers per hour, we always convert them into meters per second. The masses in this unit are always in kilograms. So I'm given a mass and a velocity, and I'm required to calculate the kinetic energy. Okay, I'm going to use my equation that we just derived, half mv squared. I'm going to substitute in, the mass was 0.150 times the speed of 35 meters per second. I'm going to square that amount, and I get a final kinetic energy of 92 joules. Okay, so there is the first sample. And there's 3 practice questions that are basically the same thing. You plug and solve. Okay, so there's questions 1, 2, and 3. Here that you can work on. I've just done this first sample. So that one's done. I'm going to leave you with those. And again, there's a bunch in the textbook. So I would take the time and work through the 2 examples that they have done for you in our textbook. Right? And then when you're done, there's 7 questions at the end of the chapter that you can be working on that use EK equals 1/2 mv squared. Okay, I'm not quite done yet. I'm almost done. Okay, the last thing I want to talk about is something called the work energy principle. Okay, and it basically says if an object changes its speed, then it changes its kinetic energy. Right? Because kinetic energy is 1/2 mv squared, so if V changes, EK changes. When I look at the difference in the kinetic energy of an object, delta EK, it will be equal to the amount of work done that was done to the object. So in order to change the speed of an object, work is done to it. And the amount of energy change that happens is equal to the work that was done to it. So that was our second equation, or our second way of determining work. We said work equals F delta D. Work is also equal to delta E. Okay, so those are our two formulas for work. All right, so let's look at the sample for 1.2b here. Here's the sample for 1.2b, and it says a 165-gram hockey puck is initially at rest, and it's going to be pushed by a hockey stick. So it's originally got a V1 of 0 on a slippery horizontal surface. The amount of horizontal force is 5 newtons. Assume that there is no friction, it's frictionless. And it says, what is the speed of the puck after it has moved 0.50 meters? Okay, what is the speed after it's moved 0.5 meters? Okay, so let's go back to one 1.2b. This is the sample. It's just a bit bigger. Okay, so I've got my hockey puck, right, and it is, 165 grams. And it has a V1 of 0. And then it's going to have a force applied to it of 5.0 newtons. And while it's got that force being applied to it, it's going to move a distance of 0.50 meters. Right? So the stick gets behind the puck and pushes the puck half a meter while it is causing the puck to speed up. Right? And when it's done, the question is, what is the final speed of the puck? Right? What is the speed after 0.5 meters? So probably you could look at this and try to come up with a number of different ways. But what I'm seeing here is an applied force, and I've got a distance that's going to be traveled. So I automatically know that work has been done to this puck because a force was applied over a distance delta D. So I'm going to start by saying work is equal to the applied force, 5 newtons. This is working a lot better now, times the delta D of 0.50 meters, and I get a work done, which is 2.50 joules. Okay, now what? Well, I know that if it has had this much work done to it, that work is how much energy changed for that puck from the time it was sitting there till the time it left the stick. Now I know that when it was sitting there, it had a kinetic energy of 0 because it was sitting there. So before the hockey stick, it had an EK equal to 0. So if work equals delta E, which equals EK at the end minus EK at the beginning, but we know the EK at the beginning was 0, then we can now calculate the EK of the puck when it leaves the stick, because I know work and delta E are 2.50 joules. EK2 is 1/2 the mass of the puck times its speed squared minus 0, the kinetic energy it had before it was hit. So again, let's substitute some of our numbers in here. I've got 2.50 times 2. Let's take the half. Just take the 2 up to that side. I'm going to take the mass, which was 165 grams, 0.165 kilograms, is equal to v squared. Again, I've taken the 2 from here up beside the 2.5. I've taken the mass from here down under the 2.5, and I'm going to solve for my speed. And the speed turns out to be 5.5 meters per second. The nice thing about kinetic energy is it's a nice simple formula. Half mv squared, half mv squared, half mv squared, over and over and over and over, to the point you realize this is ridiculously easy, right? Because it's just that same simple formula for kinetic energy for the object that's in motion, over and over and over again. Okay, so, whoops. So there are two practice problems that came just after that sample problem at the end of the 1.2b. One talks about a 1,300 kilogram car. The other one talks about a 52 kilogram ice hockey player. So I'm going to leave you with these two questions to do also. All right, so you've got a few things. There is these two questions. There are these three questions. And there are these questions here for you to work on. Most of it is all half mv squared stuff. Oops. Yeah, that's everything for today. That homework probably shouldn't take too long. So I'm going to come back and start talking about gravity. So today is Wednesday. We'll be doing gravity on Thursday. I think we probably won't need, maybe Friday if you want in the morning, we could have a drop-in session. I don't know if I will plan for a lesson, but I'll plan for a drop-in session from 10:30 to 11:30 on Friday. Some staff are calling these office hours, I guess, so I'll have an office hour at our regular time, which is 10:30. I'll send you an invite for that through, I'll let you know on Remind, and you will get an invite for it with your email. All right, and then you can, when the time comes, if you go just directly to into the hub, you can click on that team icon at the top, Microsoft Teams icon at the top of our homepage. Okay, so here is your Microsoft Teams icon. That will get you into the class. And anytime I do an online